Everyone, I'm Eliza Jean M. Dacot, and I am teaching about the abstract algebra in complex numbers under multiplication and proving that it is a group under multiplication or the binary operations under usual multiplication. Okay, complex numbers under usual multiplication. We have to follow the certain conditions. For group 1, it must be closure. Group 2 would have the associative. Group 3, identity, and the property of the group 4 is having the inverse property. Okay, let's have the next. So let us define first what is a group. So a group G denoted by G dot is a non-empty set G together with a binary operation dot on G such that the following conditions hold. Okay, so the first condition is a closure property. So let's have for all A, B element of G, the element A dot B is a uniquely defined element of G. So to have the closure property, we must have first the binary operation be uniquely defined based on the group G that we have. So second property is the associativity. So let's have for all A, B, C element of G, which belongs to G, we have A dot quantity B dot C quantity be equal to the quantity of A times B multiplied by C. So for associativity, the parentheses are being associated with one another having its groups. The third property is when we have the identity. So in the identity, there exists an identity element E in G, symbolizes with E, such that E multiplied by A, where A is an element of G, and A multiplied by E is equal to A itself for all A element of the group G. The fourth property is the inverses. For each A element of G, there exists an inverse element. So let's suppose A inverse be element of G such that when A is multiplied by its inverse, A inverse is equal to E. And it is also the same as when we have A inverse multiplied by A must be equal to E. So let us prove that the complex numbers and their multiplication is a group. We have this symbol, C star, and a dot. So the first conditions that would satisfy is, so this would be the statement, prove C star is a group under multiplication of complex numbers. So let A plus BI, which is a form of complex numbers, so as with C plus DI, X plus YI, which is an element of our group. So C star is closed under the multiplication as it provides or satisfies the property of the conditions under multiplication. So let's have for G2, which is a property of associativity. So having that denotion about the A plus BI, C plus DI, and X plus YI, let us group it together to form associative property of multiplication. So let's have the first condition under associativity, which is the left-hand side of the equations. So let us suppose A plus BI quantity multiplied by C plus DI multiplied by X plus YI. So it is equal to AC minus BD plus AD plus BC multiplied by I and quantity X plus YI. So we get that using the FOIL method, which is first, outer, inner, and last. So let us consider that I squared is equal to -1. That's why we have AC minus BD. When multiplied, BI and DI will give us negative BD. And that is simplifying the complex numbers. We have AC minus BD, factor out X, and AD plus BC, factor out Y. So it is subtraction. It's because we have distributed the X and yi to the other form of quantities. So it is equivalent to ACX minus BDX minus ADY minus BCY plus quantity ACY minus BDY plus ADX plus BCX multiplied by a complex number I. So that is... Okay, let's continue. So let's prove the right-hand side of the associativity, which is having in the property of G2, which is A plus BI quantity C plus DI multiplied by X plus YI. So we have distribute A plus BI multiplied by quantity Cx minus dy plus Cy plus dx multiplied by I. So it is obtained again using the FOIL method and separating the complex numbers and real numbers, which is denoted by I for complex numbers, and the variables a, b, c, d, and x, y for the real numbers. So simplifying the equation, we can have a plus bi will be distributed to the other quantities or other factors. We have a multiplied by cx minus dy and also a multiplied by cy plus dx times I. So another is bi will be multiplied to cx minus dy and cy plus dx multiplied by I. So it would result to quantity A multiplied by cx minus dy minus b multiplied by cy plus dx plus the real numbers that is on the left side, and the complex numbers would be in the right side, which is denoted by I. So we have A multiplied by cy plus dx plus b multiplied by cx minus dy quantity I. So simplifying it, we can have acx minus ady minus bcy minus bdx. So we distribute A on the left side of the equation, distribute it all throughout the quantities, plus acy plus adx plus bcx minus bdy quantity I. So for our final answer, it is equal to acx minus bdx minus ady minus bcy for the set of real numbers, and acy minus bdy plus adx plus bcx multiplied by I for the complex numbers. So by the solutions that we have in 1 and 2, we can have, or we can say that the quantity A plus BI multiplied by C plus DI and X plus YI is just equal or equivalent to the result that we can have by multiplying A plus BI multiplied quantity by C plus DI multiplied by X plus YI. Hence, we can prove that multiplication is associative under C star, which is a complex numbers. Okay, let's proceed to the property. We have G3, which is all about the identity element. After that, we will have G4 for the inverse. So let us prove. Let us first let 1 plus 0i be an element of C star. And for all A plus BI, which is also an element of the group C star. Now we have So we can have a plus bi multiplied by 1 plus 0i. So our target here is to get the identity element which is attainable by the assumption that we have. So we have a plus bi multiplied by 1 plus 0i is just equal to a multiplied by 1. So that is first on the FOIL method minus b times 0. So how can we get b times 0? It is bi multiplied by 0i. So we have b0i squared. So we can have minus b times 0. So plus a multiplied by 0 plus b multiplied by 1. So we factor out I, which is a complex number. So it is just equivalent to a plus bi, since b times 0 is equal to 0 and a times 0 is equal to 0. So it is similar also if we have 1 plus 0i multiplied by a plus bi. So it is equal to 1 multiplied by a minus 0 multiplied by b. So that is 0bi squared. So it is equal to negative 0 times b plus 0 times a plus 1 times b. Factor out I, which is just equal to a plus bi. So hence, we can have the identity element E exists in C star with respect to multiplication or to the binary operation that we have, and we can have E be equal to 1 plus 0i as our identity element. So, since we proved already G3, we would proceed to the last property of the proving a group in the complex number under multiplication. So G4 would have the inverse element. So let us have first, suppose we have a plus bi be an element of C star. So our target here is to find that a plus bi, which is the inverse, is an element also to the C star, such that we can pave the way in attaining a plus bi multiplied by the inverse of a plus bi, which is equal to 1 plus 0i, and it is also equal to a plus bi inverse multiplied by a plus bi. So to further to show that it is just equivalent to the inverse or identity element, we can have, suppose a plus bi inverse is equal to x plus yi, which is another form of complex numbers. So, a plus bi multiplied by x plus yi is just equivalent to 1 plus 0i. So, we would prove that it is just equal to the identity element. So, it implies that ax minus by multiplied by ay plus bx quantity I is just equal also to the identity element, which is 1 plus 0i. So, hence, we can prove that by using these equations to equate each other to prove that it is just equal to the identity element. So, we would proceed with ax minus by, which is equal to 1, which is in form of real numbers. Second equation is ay plus bx, which is part of the complex number, which is just equal to 0. So, based on that, we consider if a is not equal to 0. Then, ay is equal to negative bx and y is equal to negative b over a multiplied by x. So, considering a is not equal to 0, since if a is equal to 0, Therefore, it is undefined or it is just equal to 0. Then, we can have, now we substitute y be equal to negative b over a multiplied by x to the first equation. So, ax minus b, substituting negative b over a, which is our y, multiplied by x is equal to 1. So, simplifying it, we have ax plus b squared over a times x is equal to 1. And we have the LCD, which is a. So, a squared x plus b squared x be equal to 1. And we have multiplied both sides by a. By multiplication property of equality, we can have a squared x plus b squared x over is equal to a. So we have, factoring out x, we have a squared plus b squared multiplied by x is equal to a. And our x would be equal to a over a squared plus b squared. So that is our x. So now we would find our y since we get our x already. So using the equation that we have, y is equal to negative b over a. Our x value is a over a squared plus b squared. So therefore, our y is just equal to negative b over a squared plus b squared, canceling out a's on our equation. Okay. So, since we have the values of our x and y, thus we can have to our original equation, which is a plus bi multiplied by x plus yi. So, substituting the value of our x and y, we can have a plus bi, quantity a over a squared plus b squared, which is our x, plus negative b over a squared plus b squared, which is our y, quantity I. So, we have, simplifying it, we have a plus bi, our LCD is a squared plus b squared, so we can combine each other since our denominator is just equivalent. So, we have a minus bi. So, we have a squared multiplying our quantity a plus bi to a minus bi. So, using the factoring of numbers, we can have a squared minus bi quantity squared. So, a plus bi and a minus bi is just equivalent to a squared quantity bi squared. So, remember our factoring of polynomials. So, let's have over a squared plus b squared, copied the denominator. So, simplifying it, we can have a squared plus b squared. Since our bi quantity squared is just equivalent to I squared, since it is subtraction, it would turn to positive. So, a squared plus b squared over a squared plus b squared is just equivalent to 1. So, excluding the complex numbers, which is 1 plus 0i. Similarly, when we have x plus yi multiplied by a plus bi is just equivalent to 1. Hence, inverse element a plus bi is equal to x plus yi exists in C star with respect to multiplication, and a plus bi multiplied by x plus yi is just equivalent to 1, or we can have 1 plus 0i, where our complex number is equal to 0. So, therefore, C star under multiplication is a group since we proved the 4 conditions, which is the closure property, the associativity, the identity, and the inverse element. So that is all. Thank you. And that is for the complex.